Okay, so welcome back to our DSSEP series. We we are here today again. We have covered a lot of stuff now. We have moved from algorithms, graphs, trees, learned various types of data structures, how we can traverse the graph. Now this is our last lecture where we'll cover the data structures. We have covered multiple algorithms like greedy, DFS, BFS, and dynamic programming, complete search, partial search, binary. It's just one of many fused names. So today we'll first start with strong connectivity. So this is a component in graphs or trees. As we know, trees are components of graphs. So let's move into it. What is strong connectivity? In a graph, as I can see here, I have four nodes, one, two, three, four. In a graph, if I can traverse from one node to any other node, we say that there's a strong connectivity in the graph. We see in the first diagram here, the 1, the 2, the 3 and 4. I can start from any node and go to any node and come back. So this is called a strong connectivity. From strong connectivity, we get the term strongly connected components. What are strongly connected components? In a graph, when we traverse, like in a graph, when there we start from one node, then all the nodes that I can traverse from that particular node and return back is called strongly connected components. Now, of course, these concepts are valid for only directed graphs because in undirected graph, everything is strongly connected. If I can go to from one node to another, I can of course come back because it's undirected. In the below graph, which is much more complicated than the above graph, we can see there are three strongly connected components. From 1 to 2, we can see I can go and come back. I can go from 1 to 4 also, but I don't think we can see a way to come back. So it's not a strongly connected component. There's another one which is 3, 7, 6. And the nodes 4 and 5, we can see that there's no way to traverse to another node and come back. So these are separate strongly connected components. So these are four strongly connected components in this graph. Now we can encounter questions where we need to find out what are strongly connected components in a graph. So we'll learn about an algorithm today called Kosaraju's algorithm. Yes, you heard it right. It's Kosaraju's algorithm. It's quite funny. So let's just dive into it. Suppose we have a graph here. It's numbered like before starting this, I'm gonna talk about our lecture series. This will be our last lecture considering all the data structures we have covered. We've tried covering a lot of them. We've mentioned all the graphs, we have solved questions, and in the coming week, we'll have our final contest, which will be in collaboration with CodeChef. So I hope everyone participates. It will, along with our 10K prize pool, we'll also have three CodeChef premium subscription for top three winners free, and other participants also get the benefit of 40% discount on CodeChef subscriptions. So I hope you guys participate. Let's get on with this one. So what is Kosaraju's algorithm? When we start with a graph, in this algorithm, we'll start to depth first search. I hope every one of us is aware of depth first search, how it proceeds, just in case no one knows. Like we start from top node and we move to the most bottom node in a tree or a line, and then we return back. Yes, that's a depth first search. Like instead of spanning and checking all the nodes in a tree, we go through a single node till the bottom and we get back. In this above graph, we'll start depth first search. As when we start depth first search, suppose, and we'll note the starting time and ending time of each node. The time when we started from that node and the time it took to return back to that node. The first diagram we can see we started from node 1. At time 1, we started from node 1. When we move from node 1 to node 2, it's we can see the time is 2. It took 1 second, assuming it only takes 1 second to reach another node. At time 2, we are back at node 2. I hope everyone knows that in a depth first search, our goal will be to reach all the unvisited nodes before coming back. This is obviously a set step as we've done multiple graph algorithms. From node 2, we move down to node 5 as that's the only unvisited node that we can visit. At time 3, we are at node 5, and at time 4, we are at node 4. From node 4, we can see we can't go back to any other node. We can't find a new node. So we fall back. We come back. At time 5, it falls back to node 4. It retraces its path. At time 6, it falls back to node 3. At time 7, it falls back to node 2. And at time 8, it falls back to node 1. At each of the node, you can see at node 5, there is no other new node that it can visit. It can't go to 6, it can't go to 3, it can't go to 7. So it again falls back. At node 2, again, you can see it falls back because there is no pretty much no other node to visit. And again, the same with node 1. Now we go to another unvisited node as the graph is still not visited completely. We start from node 3, we move to node 7, and we move to node 6. These are the only three unvisited nodes. And after that, we again do a reverse function. We note down all the times of the nodes that we have visited and we write them. We try to follow it in reverse order in the step 2. So basically, let's go through what we did till now. We checked out a graph. We started from a node. For the graph, we did a depth first search trying to visit all the nodes, and we noted all the starting point time and the ending time. To be honest, we'll only require the ending time in each node, but just for the clarity, we try to put in the start time also. We wrote the all the returning time of all the nodes in ascending order. It will be much convenient to write in descending order, but like our focus will be on descending order, but for just convenience and sake of explanation, I wrote it in ascending order. Now, our step 2 will be to reverse the graph. When we have a graph in our matrix, we try to reverse the edges. Suppose there's an edge in one from 1 to 2, we reverse that directed edge from 2 to 1. Yeah. Now, on step 2, the bottom graph on the left side of the page, we can see it's a reversed graph. All the edges have been reversed. And now we again start a depth first search. In this depth first search, we'll try to start from the node that is that has the last visited time in our previous order. Like this time that we have noted, we can see the third node has the last visited time, which is 14. At the 14th second or 14th instance, we visited the third node back. So in this step for search, we'll start visiting from node 3, and again we'll proceed with depth for search. In the new graph, we can see from node 3, I can move to node 6, and from node 6, I can move to node 7. From node 7, there is no new node that I can visit. So I trace back, I fall back to node 6. Again, no new node that I can visit. I trace back to node 3. All the visited nodes have been traced back and no new node is available that I can visit. So this is it. This is my first strongly connected component. Next, we see node 7 is at 13, but that's already visited. Come on. Node 6 is at 12, but that's also visited. Now node 1 is at 8. So we start from 1, we go to 2. From 2, I want to go to 3, but 3 is already visited. Oops. So now we roll back and we go back to 2 and 1. So 1 and 2 are again strongly connected nodes. Node 5, now 2 is already visited at time 7 and 5 at time 6. We do it with time 5 and time 4 separately because from time 5, I can go to 2 or 6, but both are visited. So time 5 is my only strongly connected component with a single node. Now 4 is only left, so that's my sole strongly connected component. In this way, we derived 4 strongly connected components from a graph using Kosaraju's algorithm. Now let's talk about tree queries. What are tree queries? How we move down the tree, how we move up the tree. Just I think we've covered all this stuff, but this is just something that we'll use to make our jobs easier. And yeah, let's go. In We've learned about trees, how important they are, how they are acyclic graphs are called trees. And when we talk about tree queries, a typical thing that we'll need to know about is finding ancestors. What's the ancestor of a particular node in a tree? And there are two ways, obviously, to find it. Firstly, we can do series by series. Like, suppose in this given tree, I'm at node 8 and I want to find the second ancestor of 8. I can go one by one. Like, my second ancestor will be obviously 4, but even this method sometimes takes too long. Like, even O of n or supposedly k here, two steps might be too long. So here we'll use a pass method that we've used previously also. We have taught this previously also. This method, we'll note down all the kth ancestors of a node where k is a power of 2. In the below table, we can see I've noted it down. The kth power of ancestors, like x is the node, and kth power, which is 1, 2, 4, which are powers of 2, are the kth ancestors that we need to find. The first ancestor of 2 is 1, 3 is 4, again 4, 5 is 1, 6 is 2, 7, 4, 8, and 8 is also 4. Sorry, that 8 will be 7 here. Yeah, we messed up there, but it's all right. I think we can understand. For the second power of all the nodes, node 2 doesn't have a second ancestor. Node 3 does has a second ancestor of 1. Obviously, 4, 5 doesn't have a second ancestor as the root node is at 1, and 6 has 1 and 2. Similarly, we found out all the ancestors. Now, how do we find ancestors using this? Again, we have used this. Those who already know this can feel free to skip through this part. For others, let's just talk it out here. Now, we can see 2 and 4, but what if I want to find the third ancestor of 8? How do I find that? So, for third ancestor of 8, we'll go from 8. The first ancestor of 8 is 4, is 7. I mean 7. And we'll then go to the second. Now, the second ancestor of 7th is 4. 7, 1, 1. As you can see, the 1 is written there, and 1 plus 2 is 4. Like, we generally try to look at the middle of 2 and 4. So, this gives us the third ancestor of 8. And using this table, we can find all the ancestors of any node. Pretty much clear, right? Yeah, so let's continue. Now, we'll talk about tree traversal. When we traverse a tree, how is it actually stored in our nodes? And yeah, the we know whenever integer or any value is stored in a computer, it's stored in arrays. Arrays are series of numerical any data types which are stored in a memory in series. So suppose I have this given tree in this given diagram, I need to traverse it. So how will it be stored in our array? There will obviously be depth first search when we are traversing a tree, and again I've told depth first search repeated number of times. If we want to traverse this tree, we'll start from 1, it will process node 2, and depth first search till node 6, then it will come back, and again then node 3, depth first search from 1 to all the nodes of 1. As you can see, it will not repeat any node in the array, as we just want to visit all the nodes in our tree. It doesn't currently have any function. Now, suppose we want to know values of a subtree. Like, we want subtree queries, like a particular, I have this tree and a shorter part of this tree I want to have give queries like maybe add or subtract or anything. We'll take an example of sum of values of subtrees. So for this, there's a convenient method. For that, we need to store the size of the subtree and know the values of the subtree. Like, values means whatever the value is assigned to each node. Like nodes are the nodes I've given are just IDs or numbers. What it can be named anything, but each node has a value or a power or a cost that we assign it to. In this given node example that I've given here, I've given the node numbers and example. Again, we'll process the tree in our array. We'll in the size we'll write the size of the tree from there, including the subtree. Like let's just make you understand it. Suppose we are here at node 1. From node 1 to all its subtrees, all its roots, how many nodes are there in total? 1, 2, 3, 4, 5, 6, 7, 8, 9. In this example, the bottom example, we can see there are 9 nodes in total. So the size of node 1 is 9. Going to node 2, it has only 2 nodes, 2 and 6. So the size of node 2 is 6. And similarly, we have processed the size of all the nodes. And the third bottom table is contains the value of each node. Now, if I want to find the sum of all the subtree queries, like sum of all nodes starting from node 4, what I'll do, I'll start from node 4. I'll find the node ID in our node. We can see that's 4. I'll check for the size of that node, which is 4, and then I'll starting from that particular node, I'll add 4 values to it, 3, 4, 3, 1, which I can see. So this gives us a power of total 12, 11, and that's how you process subtree queries. Sum of values from now we'll talk about path queries. In path queries, we will focus on the sum of values from root to any other node. Instead of just small tree parts, we'll be focusing on the paths, like the connections that different nodes have to each other. That's called path. I think I'm again deep diving much more into the basics here, but I hope everyone knows this till now. We are almost at the end of the series. If I want to supposingly find values from my root node to any other node, then how do I proceed it? Here, again, I will process the tree. I'll add up the size to it. But the different thing, I'll in the value this time, we'll store the sum of the node plus sum of the parent node. That's what we'll do. In on each of the values, we won't just score the cost assigned or the value assigned to the node. We will use it and add it to the sum of the parent node. Let me explain it. Here at node 1, it has size 9 and the value of it is 4. As it has no parent node, its value will be 4. At node 2, we can see its cost is 5, but it is added to the value of the parent node, which is 1, and that gives us a cost of 4. At node 3, it is added to parent node and its cost is 7. The node 6, which is the cost of 3, here it is added to the cost of 2, because 2 is the parent node of 6. 9 plus 3 gives us 12, and that's why the value of 6 given here is 12. Now we go to 4, 7, 8, 9, 5. All the nodes have been processed in a similar way. If I want to know the value of a node from its parent node to this particular node, suppose from 1 to 7, I want to find the value of. It's given clearly in a convenient way. The value is already stored in our array and we can just retrieve it. Now, supposingly, I want to find the value from node 4 to node 7. How do I do it? From this table, just by myself, yeah. Not doing another entire new calculation. How do I do it? Just maybe give it a thought. Yes, like we'll just subtract the value of the difference between the four, parent of fourth node and parent of seventh node. Like the value stored at the root 7 node of 7 till where we want to find the power is 14. The value stored at the root from which we want to find the value is 4, 4 which is 9. So we subtract the value of 7 minus the value of 4 from where we are starting. And like just we add this value to our seventh node. Yeah, as you can see, if we start from 5 and 5, the sum should be 10. We need 10, but how do we get it? We subtract this seventh node value from the first node value, and how we can get it instantly by subtracting it from the fourth node value. Yeah, we sub when we subtract the seventh node and fourth node, as we know, the parent of seventh node is fourth node. 7 minus 4, 7 seventh node value minus fourth node value gives us 5, which will automatically be the value of fourth node, as there is nothing in between. We can check it from the size, and this 5, when we subtract it from 4, we get the value of the root node. Yeah, because initially you won't understand what the root node is. Now this root node value we subtracted from our value of 7, and we get the final answer. Yeah. Now we'll talk about lowest common ancestor. Like, we have two nodes and we need to find the lowest common ancestor between them. There are two methods in doing so. First, suppose they are not on same level, both the nodes are not on same level. In the particular example, let's take the node 5 and node 7. If we want to find the lowest common ancestor of these both nodes and they are not on the same level, we will first traverse from 7 to a node which is on the same level with the other node. Here 5 is on a higher level than 7, so we move up from 7. We see that both are on the same level now, 7 and the pointer which started from 7. We use a pointer here. We check if both nodes are same, then the least common ancestor is just same thing, or else we move both parallelly upwards. Like 5 will move up and the node starting from 7, which is currently at 6, it will move up. They both check, and on checking, the node 2 is the common node. So this is our common ancestor. The method 2 again is a tree traversal method. Again, we are traversing the tree, but this time when we are returning back, we again recount the value of the previous node. In the previous methods, we traversed the tree and we did not care about revisiting any node. In this method, we will write the revisited node again and again when we are traversing the tree. Like this particular tree given here, suppose for example, we have traversed it. We start from 1, we go to 2, we go to 5, no other node, the depth first search done. Go back on 2, again we note 2, then 6, then 8, and then we get back to 6, back to 2, back to 1, because 2 goes back to 1. Now from 1 we go to 3, then again back to 1, then 1 4 7. Here we can see we have noted the node, and here we have also need to write the depth 1 2 3 2. Now how do we check the different depth of nodes, like the least common ancestor? Suppose we are at node 5, and as we need to check between node 5 and 8. Sorry for the uh, miswritten stuff, but below 6 I need, that's assume that it's node number 8, because there's already a node 7 on the 4. So here we'll start from the node and we'll search for the first node that we want to encounter. The earliest possible time that we can see that node, we'll check it. Here we can see 5 here, I've marked it, and then we'll look for the node number 8. From 8 we'll check till 6, and between them we can see the node with the smallest depth value, which is common. We can see at number 2, we can the smallest value is that of depth is 2, and that will be our solution. One final thing that we want to say is distance between two nodes. How do we calculate distance between two nodes? That's a fairly very simple answer. So on distance between any two nodes is calculated in a very simpler trick. It's just a trick. We take the depth of the first node, we take the it added to the depth of the second node, and and we subtract the depth of the least common ancestor of both the nodes twice. Like for example, if we want to, let's take a complex example. Suppose we want to check the di distance between node 5 and node 7. Then the 7 under 4. That's what I mean, the actual 7 which should have been. So how do we do it? We go from 1, we go to 2, and we go to 5. We see that the depth of node 5 is 5. 2. We see the depth of node 7 is 2. So we add both the depths and we subtract 2 times the depth of node 1, which is 0, because that's the only ancestor they have. So distance is 4, which we can even calculate by our hands. But it's convenient to know these algorithms because it helps us in solving problems.